Come on in and don't be late. Let's learn science with Mr. Ed U Cate. G'day guys, how's it going? Well, this is another video. In the last video, 4.1, chapter 4.1, we were just simply coming up with the expression for acid and base dissociation constants. In this video, we're actually calculating the actual number for that constant. So there's going to be a bit of maths, but hopefully going step by step, it'll be a piece of cake. Well, let's just skip the textbook and get straight into a problem. Well, pretty much the entire section 4.2 is working on a couple of problems. But anyway, we're looking at chapter 4.2, it starts on page 103. And what we're doing is calculating the exact number for the dissociation constant. Remember, a high number means that it's a strong acid or a strong base, and a low number for the Ka or Kb means that it's a weak acid or weak base. Pretty straightforward. The actual question, well, the first topic is calculating the Ka of a weak acid, again on page 103. And the question is this: calculate the Ka of a weak acid, ethanoic acid, which is a weak acid, if you dissolved 0.029 of a mole of this ethanoic acid in 1 litre of water. The resultant solution has a pH of 3.5 at 25 degrees Celsius. Okay, well, first of all, we really need to know the balanced equation. From one lesson ago, you learnt that ethanoic acid, the formula for ethanoic acid can be written as that. That's more accurately mirrors or depicts the structural formula for ethanoic acid. It's got 2 carbons in it, 2 carbon acid. We won't worry about the AQs, although you do, but it's just I'm running out of horizontal width here. Whoops, there we go. There you go, ethanoic acid. So in 4.2, calculating dissociation constants and concentrations, I'm just going to work from paper with this one, just tracking what they mean by all this writing in the textbook. It starts on page 103, and the whole chapter, as I said in the intro, comes up with the actual value for Ka. So in the first instance, we're going to calculate the Ka, the acid dissociation constant of a weak acid, on page 103. So this is the question. Calculate the Ka of a weak acid, ethanoic acid, if you dissolved 0.029 of a mole of this acid in 1 litre of water. So obviously that's 0.029 moles per litre if you're dissolving in 1 litre of water. The resultant solution, after equilibrium has been reached, has a pH of 3.15 at that temperature, 25 degrees Celsius. So first thing we need to do is to write out the balanced equilibrium expression. So let's have a go at that. I'm going to omit the AQs and Ls and whatnot because I think I'm running out a little bit of horizontal space here. So the ethanoic acid is mixed with water, just like the question says, and that's in equilibrium with the ethanoate ion and H3O plus. I was actually cruising for space. I could have, yeah, I'll do it now. There we go. There we go. L and AQ. Don't forget to add those symbols in brackets in the exam. That's a really important point. So there's our balanced equation. Now let's see if it's balanced. 1 carbon here, 1 carbon there. Oh, sorry, 2 carbons here. And, yeah, that's right, 2 carbons over there. I was just tripping out there thinking there was only 1. 2 carbons, 1, 2, 2 carbons, 1, 2. We've got 1, 2, 3, 4, 5, 6 hydrogens this side, and 1, 2, 3, 4, 5, 6 hydrogens that side. We've got 3 oxygens this side, 3 that side. It's balanced. There's no coefficients, no need to place any coefficients in front of each chemical species there. So therefore, coming up with the expression for Ka should be pretty straightforward. There won't be any indexes. Don't forget, it's product concentrations, over reactant concentrations. My pen's running out. And so therefore the expression will be, zoom it out a bit. The expression will be the concentrations of these guys I don't think I've mentioned it in any video up until now, but you do know, for those of you, including me, who aren't up on their maths, there's no sign between these set of brackets and these set of brackets. Just means times. It's one product times the concentration of another product divided by, remember we don't include water because it's constant, divided by the reactant concentration for the unionized acetic acid. Okay, so that's the equilibrium expression. Okay, now don't forget, like I said, it's at equilibrium. These concentrations must be equilibrium concentrations. So an early heads up, just because we're given the concentration of the ethanoic acid at the start, that's before mixing it, you took 0.029 of a mole of the acetic acid, ethanoic acid, aka acetic acid, dissolved it in 1 litre of water. Yes, at the start you had 0.029 molar ethanoic acid, but that's before equilibrium. So don't jump in and put down 0.029 of a mole for the concentration there. It's not, because it'll be different by the time you reach equilibrium. Okay, but nevertheless, you do know the original concentration of the acetic acid. What you want to find out first, and what's easiest to actually find out, it's easiest to find out these two, quite easy, but easiest to find out the concentration of the hydrogen ions. Remember, H3O plus can be simply hydrogen ions. That's the hydronium ion. Okay, so to find out the hydronium ion concentration, we've got the pH. The pH is always equal 10 to the power of the negative, I'm a bit of a obsessive compulsive about my neatness, so here we go, I'll fix that up. It's not working too well today, but anyway, the pH, we already know the pH, it's 3.15. The pH is always equal to the negative log to the base 10 of the hydrogen ion concentration or hydronium ion concentration. We know the pH, we don't know the hydronium ion concentration. So the hydronium ion concentration, rearrange this whole expression there, is always equal to 10 to the power of the negative pH. 10 to the power of the negative pH is just 10 to the power of the negative 3.15. 3.15, we grab our calculator, turn it on, we can work out what that is. You punch in 10 to the power of, it's this button here, x, little square, x, 10 to the power of negative 3.15 equals, the answer is, that's a low number, 7.10 times 10 to the power of negative 4, sorry. Let's let's be accurate about that. That should be to 2 decimal places. So that'll be 0.000708. So 7.08 times 10 to the power of -4 moles per litre. So that's our concentration for acid. We now know the acid concentration. Now I've just got to find out, and that's at equilibrium, because that pH, remember, was measured after equilibrium was reached, because it remained constant. So, question remains, what's this concentration? Well, that's pretty straightforward, because from the balanced equation, we know that after the acetic acid dissociates and equilibrium's reached, equal amounts of product is formed. So if you've got 7.08 times 10 to the -4 moles per litre of hydronium ions forming, there'll be the exact same number of acetate or ethanoate ions forming. So CH3COO negative is ethanoate ions. Will also be 7.08 times 10 to the -4 moles per litre. So now we know that. In the textbook, they get you then to, here's our old friend, to use the ice table to calculate the thing that we don't yet know, which is the equilibrium concentration for the acetic acid, ethanoic acid. So let's go and start out our ice table. So remember, ice stands for I for initial concentration. I'll just use the word CONC, initial conc. The change in concentration, and the equilibrium concentration. Okay, and remember how to do your ice table. Along the top, you just write down all of your chemical species in the equation. Acetic acid is mixed with water. That produces the hydronium ion, and wrote it down the wrong way, but anyway, according to how I wrote it before, it doesn't really matter. Okay, whether or not you draw your table, it's up to you. Might as well, since I've started. There we go. The initial concentration, as stated in the question, was 0.029 moles per litre for the acetic acid. Water is a liquid, so it has an initial concentration of 1. And of course, at the very start, right at the very start, as soon as you mix the acetic acid with the water, there's no hydronium or acetate ions at all. There's 0. Now the change in concentration, well, in the textbook it says that after you mix the weak acid with the water, the textbook shows it as a -X, because I'll draw a picture here to show you. So if you started out with that amount of ethanoic acid at the very start, well, after that amount of ethanoic acid dissociates, you'll end up with slightly less ethanoic acid. The part that I shaded in dissociates into its ions. So a little bit is lost from the original amount of ethanoic acid, and that's why it's a negative. The concentration of ethanoic acid goes down by how much? Well, we don't know that yet, by X. Whereas at equilibrium, the concentration goes up by X. Now we know the value of X. We actually already calculated that in down here. 7.08 times 10 to the negative 4. 7.08 times 10 to the negative 4 molar. Same with that. 10 to the negative 4 molar. So, because that's our calculations before, we got this value from the pH, and we just deduce that we must be getting a similar molarity of acetate ion. So from the balanced equation, 1 mole of ethanoic acid produces equal moles of the product. So if you're getting that molarity of product forming, adding that, well, it must be take that same amount times 10 to the negative 4 molar. Okay, so we know, by the way, that that same molarity is the equilibrium concentration. Now we just got to work out what our equilibrium concentration is for the ethanoic acid. So let's check that out. Can you see that it's simply this? It's the original concentration minus the concentration that was lost by the fact that it dissociated into these two ions. Hope you can see that. So let's just do that quickly now. It's just so the concentration of acetic acid at equilibrium equals 0.029 molar minus the 7.08 times 10 to the negative 4 molar. And you can punch that into the calculator if you like, but just to save time, that will equal 0.028 moles per litre. Now, just pause for a second. Can you see why acetic acid is a weak acid? At the very beginning, it had a concentration of 0.029 molar, moles per litre. At equilibrium, it finishes with not much less taken off, 0.028 moles per litre. It only loses a small fraction of molarity because it's a weak acid. Not many particles dissociate. Okay, so now we're almost there. If we rewrite our equilibrium expression, Ka is equal to CH3COO. It's important in the exam not to cut corners with writing. It was very tempting for me to just simply omit rewriting the equilibrium acid dissociation expression, but don't be lazy. Okay, we know the value of that. It's 7.08 times 10 to the negative 4 times 7.08 times 10 to the negative 4 divided by 0.028 molar, molar, molar. Okay. Now, because you know from your maths that a number multiplied by itself is just squared. So it'll be 7.08 times 10 to the power of negative 4, all squared, divided by 0.028. Okay, And after punching that into your calculator, it comes out to 1.8 times 10 to the power of negative 5. Okay, you'll be right with that with the calculator, won't you? Yeah, look, seriously, if you can't work out your how to work your Casio FX82 yet, give us a yell. But you literally go from left to right, punching all that in, arrow, 7.08 times 10, hit that button, to the power of negative 4, close bracket, to the power of 2, and then divide by 0.028. You'll be good. Now, have a look at that number. Ka for acetic acid is calculated at that number. So if you compare with table 1, which from the chapter before, here we go, acetic acid 1.8 times 10 to the power of negative 5, pKa of 4.74. So what does that number tell you? Is that a big number or a small number? Well, it's a negative number, so it's small, it's less than 1. Negative 5, that's getting up pretty up there. That shows you that it's a weak acid. A small Ka value is a weak acid. Let's go on to another problem on page 104. There's another problem dealing with a base this time, a weak base. As usual, it's in equilibrium. So let's look at this question. We're going to calculate the pH of this weak base, ammonia, where you have prepared 0.15 moles per litre of this weak base. The Kb for ammonia is 1.8 times 10 to the power of negative 5. Well, like always, we have to come up with an equation, an equilibrium equation. Don't expect that they will give you this equation in the exam. You might have to work it out yourself. The question here has already given us the formula for for ammonia, which is NH3. We won't be lazy this time. We'll add the phase symbols in. It's added to liquid water, and that produces, that's in equilibrium with the ammonium ion, which is in solution, and the hydroxide ion. The expression for KEQ, just from this, now we're guns at this now. It's just, I won't even write the products over the reactants. It's just the product concentrations, multiply the product of the products, if you know what I mean. Product meaning times. You times the concentration at equilibrium of one of the products, times it by the other, divided by the concentration of the ammonia at equilibrium. It's got to be at equilibrium. Okay, so that's our equilibrium expression. Now, using this equilibrium expression, we can actually come up now with, we can sub in some of these values. So Kb, we know that, we're given that in the question. 1.8 times 10 to the power of negative 5 equals, now when ammonia dissociates, it dissociates into equal quantities. Now, like in the last question, because they dissociate into equal quantities, these concentrations will be the same at equilibrium. Because they're the same, we can assume that the hydroxide ion concentration is squared. One number, because they're exact same number, we know from maths that one number times by itself is the squared. Now, the reason why I chose hydroxide ion concentration is so that we can calculate the POH. And as far as the concentration of ammonia at equilibrium, ammonia is just extremely weak base, and so we can assume that the equilibrium equilibrium concentration for ammonium for ammonia, will be 0.15 molar. Okay, moles per litre. So all we have to do is rearrange this equation to find out the high hydroxide ion concentration. So we put that on one side of the equation. This one will go over there, 0.15, and when this one goes over there, it will multiply by 1.8 times 10 to the power of -5. We can work out that number times that number, punch it into your calculator, and it will come out to had it worked out before, it's in the textbook anyway, 2.7 times 10 to the power of -5. Okay, and this equals hydroxide ion concentration squared. We don't want to know the square of the hydroxide ion concentration. We want to know just the hydroxide ion concentration. Let's flip it around. Okay, let's just flip it around. 2.7 times 10 to the -5. Okay, we want to know just the hydroxide ion concentration. So if let's make it really simple for you. Let's work out what 2 to the power of 2 equals 4. Okay, 2 to the power of 2 is 4. We don't want to know, x squared equals 4. Let's work on that one. We don't want to know the value of squared. We want to know the value of x. So the value of x wouldn't the value of x be the square root of 4? Okay, which is equal to 2. Can you follow that? So back to here, do the exact same thing. Hydroxide ion concentration will be the square root of 2.7 times 10 to the -5. Punch that into your calculator and you'll find that it's 5.2 times 10 to the power of -3 moles per litre. Okay, that's the hydroxide ion concentration. Remember that the POH is equals negative log to the base 10 of the hydroxide ion concentration. So it'll be negative log to the base 10 of what it is, 5.2 times 10 to the power of -3, and that will equal, I can punch that into your calculator and it'll come out to, I've got the answer in the textbook here, 2.3. Okay, that's the POH. Original question asked for the pH. Okay, we're almost there. To find the pH, remember the pH plus the POH is equal to 14. Okay, that magic number 14. The pH scale is 1 to 14. So therefore, we just ran out of page space there. How annoying. So therefore, the pH will equal 14 minus POH, which is equal to 14 minus, what was the POH again? POH was 2.3 minus 2.3. 14 minus 0.2 minus 2.3 is 11.7. You can punch it into your calculator to verify. So the solution for this problem is that this particular solution of ammonia with a with a original solution of original concentration of 0.15 moles per litre is 11.7. It's a high pH because it's a base, okay, and it's a weak base. Looks high, but don't forget the pH scale goes up to 14. Sodium hydroxide has pHs as high as 13 and 14. So that's still pretty weakish. It's still a base. Well, I hope your head's not spinning too much. Don't forget you can replay this video and go over it, but I will post all these sheets onto OneDrive. Watch out for them. See you later. Okay guys, the pressure's off me. It's now on you. If you could just have a go at doing check your learnings from the textbook on page 105 for this section, section 4.2, and we'll be back for one last section in chapter 4 before we start our really exciting unit on organic chemistry. Have a good one. See you later.